Alright, we are going over the review for the Unit 1 exam. Number 1, is air considered matter? Of course air is considered matter. Think about what air is. It's gases like nitrogen, oxygen, argon, things like that. So it's definitely matter, and a good way to use a definition would be it has mass and takes up space. Small amount of space, small mass, but nonetheless air still has mass and takes up space. Think about blowing up a balloon. Number 2, what would be the correct measurement? So the increments go by the ones place, so this is between 4 and 5, but we would estimate out one more digit. So maybe 4.6 or 4.7 centimeters. Density. So for the density problems, you're actually going to have the density circle. Density, mass, volume. But you have to remember how to use it. You cover up what you're looking for. This is a multiplication, this is a division, this is a division here. So for the first one, you're looking for density. So density is mass divided by volume, and the specific mass in this problem is 232 grams. So we divide that by the volume, 25.8 milliliters, and we get 8.99 grams per milliliter. So we look up at this table up here for what it's closest to, and it appears that this is copper, because copper's is 9.0 and this is really close. Number 4, what's the volume of a 30-gram sample of gold? Well, to get volume, you need to do mass divided by density. So we take the mass, 30 grams, divided by the density of gold, which is 19.3 grams per milliliter. 30 divided by 19.3 comes out to be 1.55 milliliters. Describe the function of a graduated cylinder. A graduated cylinder accurately measures the volume of a liquid. So how much space it takes up. Describe what it means when something is labeled AQ. That means that it was dissolved in water. How is this different from a substance labeled with an L? That is usually something that was, for example, heated up to melt, and it's now in its liquid form. Some things are already in their liquid form at room temperature, like water, for example. But other things like a metal, maybe aluminum metal, if you heated that up, it would melt into a liquid. Or sugar. If you heat up sugar, it would melt and turn into, it's like a caramely brown liquid. But if you throw sugar into some water, that's different, because that's just dissolving in the water. You're not heating it up or anything to change its phase. What are the symbols? So you should still remember your symbols. Okay, so those are just 4, but I would go back and review all of them. Number 8, determine the number of elements and atoms of each for the following compound. So this one has 2 sodiums, 1 carbon, and 3 oxygen. Number 9, name any element that has similar properties to cesium. So you could choose anything else in group 1A, since cesium is in group 1A. So anything in that first column. So things like lithium, sodium, potassium, rubidium, francium. And for the explanation, you would say they are all alkali metals. And elements in the same group have similar properties. properties. You wouldn't choose hydrogen for that one because hydrogen's kind of an exception. Even though technically it's listed in the same group, it's a gas, so it's not one of the alkali metals. Number 10. Identify one element that belongs to each of the following families. So we just did that because we just were looking at the alkali metals, so anything in group 1A, for example, lithium. The noble gases are on the opposite side of the periodic table, group 8A, the far right. An example would be helium. Transition metal are that whole middle block of elements. So you'll have to look at the periodic table in class. This section's actually labeled for you. Copper would be an example. The halogens are group 7A. So things like chlorine, fluorine, bromine. And the alkali earth metals are next to column 1A. Column 2A, that's got things like beryllium, calcium, magnesium. Number 11, identify the following as a metal or a non-metal. So how are you supposed to figure that out? Well, you look at the periodic table, and everything to the left of that zigzag is a metal, with the exception of hydrogen, because hydrogen is just a misfit. Everything to the right of the zigzag is a non-metal. Okay, so looking these up, chromium's to the left, so it's a metal. Oxygen's to the right, it's a non-metal. Tin is to the left, it's a metal, so is lithium. And neon is to the right, so it's a non-metal. Now you might be saying, what about the metalloids? Those are things that border the zigzag, they're touching that zigzag. Those have properties of both. Number 12, describe the most current model of the atom. Describe one of the earlier models and some key differences between the two models. So let's start with an earlier model. They used to think that atoms were just small, dense, no charge, hard little marbles, basically. So they didn't know a lot. Then they had some more scientific discoveries with new instrumentology, and they came up with the plum pudding model, which said it's like a plum pudding where the raisins are negatively charged electrons and the pudding is just some positive stuff. Then along came the gold foil experiment, where they determined that atoms are mostly empty space, but they have a small, dense nucleus in the center, and they drew the electrons surrounding that nucleus. Then they said, okay, maybe the electrons orbit the nucleus just like the planets orbit the sun, and they figured that out because through experimentation, they figured out that electrons have specific distances that they live away from the nucleus. And the best way that we represent the model of the atom is to show a tiny little nucleus, and then we represent the electrons as a cloud, a probability cloud. And we know that the electrons take up most of the space of the atom, although the nucleus takes up most of the mass. Number 13, when you heat up a sample of helium and observe it through a spectroscope, you see multiple bands of light of different colors, including red and blue. What's happening inside the atom that causes this? Include a diagram. So first I'm going to draw a helium atom. It's got 2 electrons in that first shell, okay, and there are all these other shells. And when you heat it up, electrons jump up to higher energy shells, and what goes up must come down. When they fall back down because they were unstable, they release a photon of light. Okay? So if you've got, here's another helium atom, because you've got lots of helium atoms that you're exciting at once. If it makes a small jump up, maybe just one level up and falls back down, that releases a longer wavelength of light, a lower energy color like red. Versus over here, this first drawing, it jumped up 2 energy levels and fell back down. So maybe that would be enough energy to that we would see it as blue light. When we look through the spectroscope, we can actually see these individual bands that are caused by these electrons jumping and falling back down. Number 14, write out the electron configuration and the noble gas shorthand for silicon. So you can refer to my earlier video that goes through how to do electron configurations if you're a little rusty, but for silicon it should be 1s2, 2s2, 2p6, 3s2, 3p2. If you add up the little numbers, they add to 14 because silicon is number 14. And the last noble gas before silicon is neon. So you would write neon in brackets 3s2, 3p2 for the shorthand. Notice that the outer shell must be the third shell. It's the biggest number out front. And there are 4 electrons in the outer shell, which all makes sense because silicon is in group 4A. So it has 4 valence electrons. Arsenic's a little bit longer. It goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember the D block, it always skips down a shell. 3d10, 4p3. The last noble gas before arsenic is argon. So you would write argon in brackets, 4s2, 3d10, 4p3. Silver is the longest. Oh, here we go. Silver, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. The last noble gas before silver is krypton, and then you continue from there, 5s2, 4d9. So how many valence electrons does silver have? 5 is the biggest number out front, so it would have 2 in its outermost shell. Then it asks you to answer questions about number 80. Well, that is mercury, Hg. Since it's number 80, it's got 80 protons. Let's skip down to its neutrons. Let's see, I'm not looking at mercury's mass right now, but it must be 201 if you round it to its most common. So looking at the number at the bottom of number 80, it must be 201 point something. Because if you do 201 minus 80, you get the number of neutrons, which is 121. Electrons match the number of protons as long as it's a neutral atom, which so far in this class they've always been neutral. Valence electrons. Let's skip down to the noble gas configuration. It would be xenon in brackets, and it would be 6s2, 4f14, 5d10. Now you might be freaking out and saying, what? We didn't do anything with the F subshell, and this won't be on the unit exam. Won't be on the exam. But we can still use this configuration to help us figure out how many valence electrons it has. Biggest number is 6, and there are 2 in there, so this would be 2. And for the core electrons, we would do 80 minus 2, that's 78. Name one other element with similar properties. You could say anything in its little vertical group, Cd, Zn, cadmium, and zinc. And this element is to the left of the zigzag, so it would be a metal. Number 16. An atom of magnesium that has 14 neutrons would have what mass? Well, magnesium's number 12. It always has 12 protons. So if it's got 12 protons and 14 neutrons, we add those together, and that's 26. That would be its mass. So its symbol would be Mg, 26, and 12. You would name it magnesium 26. one, it's number 11, so that is sodium, and we would add the 11 plus the 12, that's 23 for its mass, and the number of protons always goes in the on the lower left. How about these average atomic mass problems? You always take each mass times how often they occur. So 234 times, but move the decimal 2 back because this was a percentage. So 0.0001 plus 235 times 0.0071 plus 238 times 0.9928. And if you add all that together, it ends up being 237.98 grams per mole, or you could write AMU. Either one of those units works great. And this makes sense because 99% of the time it weighs 238. And once in a while, 0.01% of the time or 0.71% of the time, it weighs less. Those are slightly bringing the average down from 238. Number 19. What happens to the mass number and atomic number for alpha decay? In an alpha decay, the atomic number goes down by 2, and the mass number also goes down. It goes down by 4. That's because in alpha decay you're essentially losing a helium nucleus, 2 protons and 2 neutrons, which adds to a total mass of 4. Beta decay, the atomic number goes up by 1, and trick question, the mass number actually stays the same. This is because all that's happening is a neutron is being converted into a proton. So they weigh the same, it's just the neutron caused the atomic number to go up by 1 now that it changed into a proton. So how about writing out these equations again? Gold 201. Gold is number 79. So if this undergoes a beta decay, we draw the little beta symbol. We know the mass is going to stay 201, but the atomic number in the beta decay goes up by 1. So now this is a mercury. You have to look at the periodic table and figure out what the new symbol is that you need to write there. Alpha decay for platinum 192. I'm looking up on the periodic table, platinum is number 78. Remember that an alpha particle has the numbers 4 and 2 associated with it, and this is like the Rice Krispie treat. You're losing 4 from its mass. It was 192, so now it's 188. 78 minus the 2 because you lost 2 protons. This is now element 76, which if you look it up, it's osmium. How about a fusion? Helium 4, so the 4 goes in the upper left because that's the mass, and helium's number 2, so that goes in the lower left. Neon, this neon has a mass of 20 and it's number 10. If we add those together, 20 plus 4, 2 plus 10, we've now got a magnesium atom. What's the difference between a chemical and a nuclear reaction? In a chemical reaction, you're rearranging entire atoms. Atoms are moving around, combining with new atoms, splitting apart, switching places. But in a nuclear equation, you're actually rearranging the protons and neutrons within atoms. So that's actually changing their identity. That's really different. A chemical reaction can have property changes because new compounds are being formed, but a nuclear equation is changing the individual tiny atoms themselves. How about fission versus fusion? Fission is when an atom is split. Fusion is when 2 small nuclei come together and make a larger nuclei. should really draw this one. I'm going to redraw this one. Okay, what they both have in common is they both release lots of energy. Differences: fission is what happens in a power plant. Fusion is what happens in the stars. Both can be used to make atomic weapons. Half-life. How long is it going to take 120 grams to decay to 7.5? The half-life is 3 minutes. Well, after 3 minutes, only 60 grams remains radioactive. After another 3 minutes, only 30 grams remains radioactive. After another 3 minutes, only 15 grams remains radioactive. And after another 3 minutes, 7.5 grams. How long did that take total? 3 plus 3 plus 3 plus 3, that took 12 minutes. So that would be the total answer. All right. Grams to mole conversions. What if you've got 700 grams of potassium? Remember, you write out what you know. Now we want to convert this into moles. Do we know any conversions? Sure we do. We can figure out how much 1 mole of potassium atoms weighs by looking at the periodic table. That's what the number at the bottom of the squares tells you. It tells you how much 1 mole's worth of that atom weighs in grams. So 1 mole of potassium weighs 39.1 grams. So you've got way more than a mole because you've got 700 grams. So how many moles do you have? 700 divided by 39.1, because you multiply everything on the top divided by everything on the bottom, you've got 17.9 moles of potassium. Next one. This one's a little tricky. It says you've got a sample of iodine and a sample of copper that contain the same number of moles. If the copper has a mass of 127 grams, how much does the iodine sample weigh? Let's start by writing what we know. 127 grams of copper. Let's get that into moles. There are 63.55 grams of copper in 1 mole for 1 mole of copper atoms. So if you've got 6.02 times 10 to the 23rd copper atoms, they weigh 63.55 grams. I just got that number from the periodic table. Multiply across the top, 127 times 1 divided by 63.55. That comes out to be 2 moles. It said we had the same number of copper moles as we do iodine moles, so we've got 2 moles of iodine. How much is that going to weigh? Well, 1 mole of iodine, if I look it up, it weighs 126.9 grams. So multiply across the top 2 times 126.9, that comes out to be 253.8 grams worth of iodine atoms. So again, the wording on that question was a little bit weird, so if that's what's confusing you, don't stress out too much. It's pretty straightforward on the exam, although you should be able to tackle something like that. Alright, number 3 is a little different. We're starting with moles. 3.5 moles of nickel. How much would that weigh? Well, let's figure out how much 1 mole of nickel would weigh first. 1 mole of nickel, according to the periodic table, weighs 58.69 grams. You've got 3.5 moles, so multiply across the top, divide by the bottom, it would be 205.4 grams of nickel. Number 4, which would contain more atoms, 10 grams of copper or 10 grams of carbon? Well, let's think about how big the atoms are. 1 mole's worth of copper atoms weighs 63.55 grams. 1 mole of carbon atoms weighs 12.01 grams. So carbon atoms are smaller. So if you had equal amounts of both, which one actually has more atoms? The answer would be carbon, because it takes more of these smaller atoms to equal 10 grams. Number 5. Given the following info, identify the element. 15 moles weighs 104.12 grams. Well, we're used to grams per mole, so let's figure that out. 104.12 grams per 15 moles. We're used to grams per 1 mole, I should say, so we need to divide here. That comes out to be 6.94 grams per mole. What element weighs 6.94 grams for every 1 mole of its atoms? The answer is lithium if you look it up. Number 6, you mass out 0.1 moles of CuSO4. How many grams would this be? Well, we've got to figure out how much 1 mole of CuSO4 weighs, because we only have 0.1 moles of it. So we go off to the side and we say, okay, copper weighs 63.55 grams, plus there's the sulfur, that's 32.07, plus there's 4 oxygens, so 4 times 16. You add all of that up, and it adds to 159.62 grams. Now multiply across the top, divide by the bottom. 15.96 grams of copper sulfate, CuSO4. Number 7. Student dumps 123 grams of HCl into some water. How many moles did they add? We've got to figure out how much 1 mole of HCl weighs so we can determine if we've got more or less than a mole. So again, go off to the side. Hydrogen weighs 1.01 grams per mole. Chlorine weighs 35.45. That makes the molar mass 36.45. 458 if you're using a longer number here. Multiply across the top, 123 times 1 divided by 36.458. Answer, 3.37 moles of HCl. Finally, the last question is just a lot of work. What's the molar mass of TNT? 7 times 12.01, that's the mass of carbon, plus 5 times the molar mass of hydrogen, plus 3 times the molar mass of nitrogen, plus 6 times the molar mass of oxygen. I got 227.14 grams per mole. Alright, good luck.